Okay, here we are then. Latest modelling one. We've got an exciting one today. Hot air balloon flight. Um, you're advised to spend more than 50 minutes on this part. The task is about the flight of a hot air balloon. So let's have a good read of what's going on to start with. First thing I'm picking up as I'm reading this is journeys in 4 parts. So they're clearly telling me this for a reason. Part 1, Part 2. Let's read them all individually. In part 1, there's a lift-off. The balloon leaves the ground and rises. Kind of makes sense to me. For part 2, there's the flight. So I anticipate that'll be slightly longer. Part 3, then the balloon descends quite quickly. That's quite alarming. And then part 4, I'm now thinking the balloon descends slowly. Oh, that's good. Before then landing. Okay, nice. Okay, this journey is at sunrise. That's a nice bit of detail. Maybe that will come a little bit clearer later. For part 1, a model for the height of the balloon above the ground, h meters, t minutes after liftoff is h is equal to 480 brackets 1 minus cos 20t degrees for 0t up to 9. Okay, a lot of information there. Let's just try and unpack this a little bit. A couple of things that I'm picking up on that I think are really kind of important. The first thing, degrees. We're used to using degrees, but it's always worth checking that our calculator's in degrees. I can see mine already here. It is in degrees, so that's fine. Now, we're given this, and we don't need to do a great deal of thinking relative to this, this function that we've been given, because our calculator is going to do that work for us. So it's asking us for part A, and we seem to have this duplicated, but that's fine, to sketch the graph for height h from t values from 0 to 9. So that is the first 9 minutes. This is in minutes. Okay. Questions like this, the units are always really helpful to know. So let's just reach for our calculator then. Let's get this in. Add a graph. Now, what does it look like? We've got, just double check again, degrees, we're all good. 480 multiplied by. It's always worth putting that multiplication on the TI Nspire. Sometimes it's an issue. So 1 minus trig cos of 20. Again, I'll do the multiplication. And instead of t, we're going to do it in terms of x's. And, well, that's it, isn't it? Let's just close off my brackets and see what it looks like. Okay, marvellous. We've got this function here. First thing I'm noticing is, well, this doesn't look quite like the scale that I want. There's always some clues in the question. So here we're asked to go from 0 up to 9, and that kind of works. I've got 0 to 10 here, but it goes as high as 960. So that's my first clue. So let's have a look at this. First thing I'll do, because I want to go up to 960, maybe I'll go slightly beyond, maybe I'll go to 1000. Ooh, lovely, look at that. Okay, so it looks like from 0 up to 9, it's doing something like this, and it might be around here at the peak that the 9 finishes. But what we can do is we can be really sure about this, and we can change the domain of this function. So I might just get the calculator to plot for me the values from 0 to 9, just because that's what we're asked to plot here. And I can get a real sense of what the shape is and where it's going. So the way I do that is control and equals, giving us all these options here. Now the one I want is this. That gives me then a chance to put in the domain. And the domain I want here is I want my x values from 0, and I want it up to x values up to, and then same symbol up to 9. And look at that, we've just got from 0 to 9, and there it is. Okay, so I might just move this across a little bit, and we've got this that we need to plot. Now, this is going a little bit, just to ensure I get the right shape, this is the sort of thing that I'm looking to put into here. So we've got that cosine curve that we're used to. It comes through 0, 0, it's coming up here, and then it's levelling off at about 9. It looks like it's 960. Let's have a little look at what that point is there. Let's analyse the graph, see where the maximum value is that I've got. Okay, so that highest value is 9,960. So I just want to make sure that these align. So I'm just being quite, just having to check. Does that align? Yeah, it's not too bad. And 9, yep, and I've got the nice shape that I wanted. That's okay. I'm quite happy with that. Okay, let's move on. Find the height of the balloon 3 minutes after liftoff. Well, that's going to be quite straightforward with my calculator, because I can hit Control T to get my table of values, and after 3 minutes it's 240. Okay, there's my calculator's doing all my work for me. For part C then, find the increase in height between 3 minutes and 6 minutes after liftoff. Well, I need to find out what it was at 6 then. So at 6 it's 720. Minus the 240, which I think I can do in my head, to get 480. Okay, part D. Find the average speed at which the balloon is rising between 3 and 6 minutes after liftoff. Give your answer in meters per second. I think it's really easy to not read that little detail there. So our distance, we know it's 480. The time is equal to 3 minutes. Now, if we're dealing in meters and seconds, the 480 was in meters, so we need to do our speed as 480 over 3 times 60, because that's how many seconds it is. So I'm going to be dealing in seconds. So now let's go back here. Let's insert a calculator, because I can't do this one in my head. And I want to do 480 divided by 3 times 60. Oh, 8 over 3. What's that giving me? A value of 2 2/3. 2.6 recurring meters per second. Okay, part 1 is complete 9 minutes after liftoff. That makes sense with what we've been dealing with, because we've been dealing with this values from 0 to 9. Use the model H in terms of t to show that the height of the balloon at this time is 960 meters. Okay, so, well, we've kind of already done this work in many ways. I suppose what I'm thinking is what we want to do is, we did it here, finding this coordinate, 9 is 960. I think I would try and illustrate and communicate that I'm inputting 9 into the function. So where's my function? It's over here. So 480, 1 minus the cosine of, what does it say, 20t, going to be 20 times the time being 9 is equal to 960. So yeah, that's what we've input and that's what we get as our answer. Okay, nice. For part 2, the table shows the heights of the balloon above the ground in L meters, T minutes after liftoff. Jolly good. 9 up to 15. Okay, so this part 2 is almost in 2 sections. It seems to be saying a steady height there of 960, which we can kind of see down here. And then it's increasing up to the 20-minute mark with a height of 1095. Okay. So on the grid, complete the scatter diagram. So we're just plotting points now. Okay, some easy marks. So 16, 987, 960, 970. Around here. 17, 10, 14. Is around here, I think. 18, 10, 50, 68. No. I missed a 1041. Oops, so that was 1068 there. Let's erase that. And let's go with 18, 1041 I missed, which should be here. And then 20 is 1095, which is just around here. Okay. Plotted those points. So that's nice. Right, between 15 and 25 minutes after liftoff, so that's what we were just looking at, wasn't it? Between 15 and, yeah, so that's what we've just plotted. The beam rises at the same rate, it then travels at constant height for 10 minutes. Okay, complete the list of linear functions for part 2. Okay, so we need to describe this bit here for the first section, then we need to describe this bit here, and for what I've just read is then it continues at, what kind of a highlighted colour is that? That's better, at a height here, so it's going to continue there. So that's what we're trying to ask us. So the yellow section, from 9 to 15, well that was just at 960, wasn't it? So let's just write that in. Okay, now we need to work out what the function is that's going to map a value of 15 to this point, 16 to this point, and so on. Now what I'm going to do is I'm going to get the calculator to do this work for me again. And this time I'm going to insert a spreadsheet, and I'm going to do a linear regression, just to make sure I'm not making any errors. So let's put in a spreadsheet. Now the x values I'm interested in were 15, 16, 17, 18, 19 and 20. And then my y values I want were 60, 97, 1014, 1041, 1068. Oops, keep trying to put that in wrong. And 1095. Let's do some statistics, some stat calculations, and let's do ourselves a linear regression. My x values are x, my y values are y, and yeah, you can go there, that's fine. Marvellous. Now it's saying that in mx plus b, my m value is 27 and my b value is 555. So I can put that in here. So L is equal to 27 was the gradient, lots of t in this context, plus the 555. Okay. Now, for the last bit, now I need to just unpack what this is saying here. It then travels at a constant height for 10 minutes. So that's going to be from 25 up to 35. And what height was it at? It was this height here, which is 1095. 1095. So cool, I could do, just thought of that, we could plot all this on here, couldn't we? Why don't we add some of this so we can see what's happening? So Control T. So let me put all of these functions in here. So let's add a new one, press the tab button, and we can put in 960. 4, again, define my domain, x values from 9. Well, this is going to be cool. Up to x less than or equal to 15. Nice. Okay, we need to go a bit further. Oh, no, we need to go a bit further this way, don't we? It's not gone up anyway. Let's go up to 35, that's where I'm going ultimately. Here is my balloon journey, look at this. Right, now from 15 to 25 it's doing this, so let's put that one in. Tab to put in a new one. 27x plus 555. And now again, I just need to think about this domain. Now I want from 15 up to 25. Let's go a bit higher now. This is our balloon rising in the sky. Look at this. And then now it's going from 25 to 35. And no, I didn't need to press Control. I meant to press Tab. That doesn't matter. missed something. Tab, there we are. And now I need to go 1095. So my balloon is now going at this height for, again, we need to put the domain, now from 25 to 35. So this one, 25. X up to that makes me think I've got an error here. Let's go back and have a look. A jolly good thing to do to help me see that I've made some sort of mistake. Something looks like it's gone wrong. From 25. Ooh, so from 15 to 25. From 15 to 25 minutes after the balloon rises at the same rate, then travels at a constant. So this goes on from 15 to 25 minutes doing this. So it doesn't stop here at 20, like I've drawn on the highlighted section here. It actually continues rising. Oh, that's really helpful, isn't it? So let's try and get that right. So what would happen if I put in 25? Well, I can analyse my graph to do that, can't I? Let's analyse this and find the maximum value on graph 4 between here and here. Goes up to 1230. So I need to just change this to 1230. And there we are. Which means I'm going to probably amend this one. So this should be 1230. Okay, let's move on. For part 3, the balloon descends at a constant speed of 25 meters per second until 180 meters above the ground. 2.5 meters per second until it's 180 meters above the ground. So it's gone from 1230 down how far to get to 180? The value I'm putting this in the calculator just in case. 1230 minus 180, it descends 1050 meters at a constant speed of 2.5 meters per second. Find how many minutes it takes for the balloon from liftoff to the end of part 3 of the journey. Okay, so it's descending this far at this speed. Let's remember, speed is equal to distance over time. What do we know? We know the speed, 2.5. We know the distance, 1050, and we're after the time. And so t will equal 1050 over 2.5. And that's 420. Now that is seconds, remember? 420 seconds. Oh, I've just seen that the bit that I'm writing on, it dropped below what you can see. So let's bring it up. So I've worked out 420 seconds. We need that in minutes, because t is a value in minutes. So let's do 420 divided by 60, and we're going to get 7. So my t value is equal to 7. However, it's saying how many minutes it takes from liftoff in bold. So from liftoff, we've used 35 minutes so far, and we need to add another 7. So 35 plus 7 gives us 42. There's my answer there. Okay, question 8. For part 4, model for the height above ground d meters of t after the liftoff is this. Jolly good. Find out how many minutes after liftoff the balloon lands. Let's put it into our graph. The only sensible thing to do, isn't it, at this stage? So we need to increase where we're going. So 35 up to, I don't know, let's go up to 50. So we can see what's going on. Create a bit of space. Now the one that that bit that I've just put in, that kind of doesn't matter. So what we've just worked out, it drops down. So if you imagine there'll be a straight line going down here, and then we're expecting it to level off and land in some way. And it's that leveling off and landing that we're interested in now. So let's just put in this function. So press tab, and we've got, because this is as a fraction, I would input it as a fraction, so press control and the divide sign, so we can just make it look exactly like it does on the function. 450 over x minus 40.125, and we can subtract 60 from that. And like we said, we would expect it to come down here, and then we've got this nice tailing off, which is a nice soft landing. That's what we're expecting. Okay, and this is for, from what we've just worked out, x value is greater than 42, wasn't it? Yeah. So let's just say that we want this to have, oops, how do I read that? It's this one, no, it's not this one, it's this one, sorry. It's this one, and I want this to be now x values, which are greater than 42. This is the only bit that we're interested in here. Let's just move this a little bit. Oh gosh, that's in my way now. It's okay. So I can move it. There it is. And I'm interested in where it lands. And my calculator again can do this for me. Tell me where it hit 0. On this graph, where is that 0? It's 47.630. Okay. So we're interested in where it's equal to 0. And that's what I've calculated. Where this thing is equal to 0, t minus 40.125 minus 60, and that is when t is equal to 47.63. Marvellous. Moving on. Find the average speed of the balloon during part 4 of the journey. Give your answer in meters per minute. Oh gosh, minute per minute. Right. So that is what we're interested in here, and that is just when it's on this, sorry, part 4 is just this final part of the function, the piecewise function, so it's just this bit. So I'm kind of interested in the maximum value where it starts. So, oh, that was 180, wasn't it? Let's just check that. Should be 180. The maximum value, I think, for this graph between here and here is 180, yes. So it's travelled 180, down to 0, so it's gone distance is 180 meters, and the time is 47.63 minus 42. Minus 42, 5.63 minutes. Now my units are consistent with what I want. I want meters and I want minutes, so I can just put it into my distance over time. So I need to do 180 over 5.63 to get my answer. 31.97 meters per minute. I suppose that's quite a nice measure. So it's going to travel 31 meters every minute. Might give you a feel for kind of how quickly that's descending on average. Are we nearly done? We must be close. Okay, part 9. Another journey is at sunset. The balloon creeps. Oh gosh, okay, sunset. So another journey, something different. The balloon completes part 1 of the journey in 7.5 minutes. At the end of part 1, the height of the balloon above the ground is 960 meters. The model for part 1 is this, from 0 to 7.5. Find the value of k. Okay. So what we're interested in is the height that it reaches at the end here. So at the end, the t value is 7.5, and it's going to equal 960. So what I might do for that is I might say then the height of 7.5 will equal 960, which implies that 960 will equal 480, 1 minus the cosine of k times 7.5. And we need to work out what that k is in the middle here. Right, I've done everything on my calculator. I'm not going to break habit. I could do some nice algebra here, but let's just get it to do it for us. So menu, algebra, let's do a numerical solve. So we want to end solve this thing. 960 is equal to 480 brackets 1 minus trig function, the cosine of k, which is going to, I'll call it x in this case, times 7.5. I've got 3 brackets to solve, and I want to tell it to solve for x. I think this is going to work. Not quite set this up right, have I? So I think here I need to say solve for x, and then close my bracket. There, jolly good. 24, thank you. In part 2, the first 6 minutes of the journey are at a constant height of 960. Okay, so that's the height that we reached here. Then the balloon rises 2 times as fast as question B, 6b part 2. 2 times faster. So therefore, 2 times, how fast did it go up? It went up by 27 meters every minute. So let's do 27 times 2. 2 times 27. I'm going to trust myself to do that in my head. 54. And change the model in question B part 2 so it models this part of it. Okay, so we need the whole thing. So y is equal to 54t plus something that we don't. Be careful with this final bit because we want 54t plus b, and it would be easy to make a mistake of putting in 7.5, which is a mistake I may or may not have made. So it's not 7.5 because it would be easy to miss this thing where it says that there are another 6 minutes of the journey at a constant height of 9.6. So it's going to be this 7.5 plus this 6 minutes. So what I'm looking at is a time of, to achieve this starting point of 960, it's got to equal 54 multiplied by 7.5 plus 6. Plus b, which is 960 minus 54 times 13.5 will tell me what b is going to be. So I need to do 960 minus 54 multiplied by 13.5 to give me a b value of 231. So now we just need to write it in terms of height and time. So instead of a y, I should probably use an h. So let's do it in our final answer. H will equal 54t plus 231. And there's my final answer, and I am